Okay, so welcome everybody to this new DaSCI seminar. Today is my great pleasure to introduce Roy Schwartz. He's a senior lecturer at the School of Computer Science and Engineering at the Hebrew University of Jerusalem. Roy studies natural language processing and artificial intelligence. And prior to joining his current institution, Roy was a postdoc and then a research associate scientist at the Allen Institute for AI and at the University of Washington, where he worked with Noah A. Smith. Roy completed his PhD in 2016, where he worked with Ari Rappaport. Roy's work has appeared on the cover of the Communications of the ACM and has been featured among others in the New York Times, MIT Technology Review, and Forbes. Today, he will talk about green AI and will discuss recent approaches for reducing the computational cost of AI techniques. I want to thank again Professor Schwartz for very kindly accepting our invitation. And whenever you are ready, the floor is all yours.
Thank you, and gracias por la invitación. I'm really happy to be here. Just a couple of words about myself before I get started. So I'm, as Pablo said, I'm a senior lecturer at the School of Computer Science at the Hebrew University of Jerusalem. And I study mainly artificial intelligence and with a focus on NLP. And in particular, I'm interested in understanding AI models, revealing their biases and making them more sustainable. I will mostly focus on the third topic today, but we have a lot of time. So if you're interested in other topics, I'm happy to chat about them. And in general, feel free to jump in and ask questions if anything comes up. I won't see you, so either raise your hands or say something because I can only see one person. But I'm really happy for questions along the way. Okay, so let's get started. So LLMs today, this is no secret, are arguably, or maybe not even arguably, one of the biggest breakthroughs in recent or even more recent history. We have tools coming out almost on a daily basis that are getting in very, very impressive results. And one thing that characterizes these models is the first L in LLMs, which is large language models. And indeed, they're becoming larger and larger. This is one of many similar graphs that you can find online that shows the growth of the LLMs that used to be called just LLMs, and now they're called LLMs. This one is between 2018 and 2022, where we see a 5,000x growth in just 4 years in the size of the state-of-the-art language models that we have, starting from Elmo in 2018 until I think this is Palm in 2022. And this trend of models getting larger and larger was the focus of a piece that we published a few years ago titled Green AI. This was work with colleagues at the Allen Institute for AI. And so in this work, we talked about two main things. One is this process that we refer to as red AI, of taking a model and just increasing it in order to improve your results. So when we talked in particular about two main problems that come up when you do that, one relates to inclusiveness and the other to potential environmental effect. And we talked about an alternative, which we called Green AI, that promotes efficiency as a core evaluation for AI, and talks about enhancing reporting of computational budgets. Now, in this, the first part of this talk, I will try to briefly walk you through both the concept of red AI and what are the problems of getting models larger and larger. Although this paper was written a few years ago, I think much, if not of all of it, is still highly relevant. And also talk about Green AI. And in the second part of this talk, I'm going to talk about two of our most recent findings on the topic of efficiency. One talks about reducing the memory footprint of large language models, and the other asks arguably naive question, but I will show that maybe not so much, that can we maybe settle for small LLMs and maybe they can do as well as large LLMs. So I'll get started with the first topic of red AI. And again, talking about problems with scaling, the first thing that comes to mind is the problem of inclusiveness or exclusiveness, because as models become more and more expensive, fewer and fewer researchers around the world can afford to participate in definitely training them, but also in some cases even running them. This is just a few examples, maybe not even the most up-to-date examples. BERT, one of the first LLMs, was trained on 16 TPUs for 4 days. Just a few months later, Roberta was released, and which was trained on 1,000 GPUs for 1 day, so 2 or 3 order of magnitude more compute. And Palm, 3 years later, required 6,000 TPUs for 50 days, and then another 3,000 TPUs for 15 days. So again, the amount of compute and accordingly the amount of money required to train these models is becoming very, very expensive. And as I'm sure you all know, way beyond the reach of the great majority of researchers. And indeed, when you look at the graph that I showed earlier, who builds these models, and it's the same names coming back over and over, whether NVIDIA or Google or OpenAI or Facebook. I mean, these are the organizations that are building these tools. These are not, for the majority, not university or small startups. Again, so this raises the question of who gets to decide which tools are we building, which data they're being trained on, what are the focuses, what are the considerations, and so on. And I think this is a major problem in the field at the moment. The second problem with scaling refers to the environmental impact of scaling. And this is the seminal figure from the seminal work from Emma Strubel et al. At the time from the University of Massachusetts, where they compared the CO2 emissions of standard NLP operations and compared it to regular day-to-day operations. So for instance, she compared the training a transformer with neural architecture search to the lifetime consumption of CO2 over one average car, and found that the training operation consumes about 5 times as much as a single, or maybe as much as 5 cars during your lifetime. So this was maybe the first result that addressed this question and made a lot of impact. And many others came afterwards. And kind of, I think that we're at a place right now where we can ask ourselves, is AI really creating an environmental problem? And I think this is not a trivial question to answer. And I'll try to show different views and mainly try to enrich the discussion here and talk about different ways of looking at it. And maybe I'll start with Google's answer to this question, that they actually wrote a blog post saying that the title was "Good News About the Carbon Footprint of Machine Learning Training," and one of they made some claims that Emma Strubel's original work, the one that I pointed to a couple of slides back, was off by between 1 and 2 orders of magnitude in her estimations. And the reason she was off is because they didn't reveal the details that allow her to make an accurate approximation of the actual amount of carbon that was used. And I think my takeaway from this is that, well, we need better reporting. I mean, if the original papers had reported all these details, then maybe they could have reached a better estimation. And I think in order to really answer these questions in an accurate way, we need all competing parties to disclose this information. And so following this blog post from Google, myself and other colleagues from, including Emma Strubel but many other people, try to give our own answer to this question by considering various AI operations and running them on Microsoft Azure Cloud and computing the carbon cost of that and comparing it to daily basis operations. So if we zoom in a little bit on the results, what we see on the x-axis is different AI operations. On the y-axis, on the left-hand side, we see the amount of carbon emitted in exponential scale. And on the left, this was on the left-hand side. On the right-hand side, we see the comparison to everyday operations. So if we focus here, we see that maybe training a 6 billion parameter transformer, and we only trained it, I think, maybe 10% of what it usually takes to converge such a model, is roughly equivalent to the 1 yearly home energy consumption in 1 US yearly home energy consumption. So again, is this a lot? Is this maybe this is a reasonable price to pay to train our models? I think these are questions that require discussion, but at least they require again, reporting. We need to be aware of these costs, and then maybe we can make the decision whether these are legit or not legit prices to pay for this, but at least we need to know. And I think kind of to summarize this discussion, we have some evidence by some organizations about the most expensive experiments. And the experiments I show you in the previous slide, we now have evidence that our most recent models consume maybe 2 or 3 orders of magnitude more CO2 than that. So maybe the largest language models we have consume roughly as much as maybe a small neighborhood or maybe a small town would in a given year. So again, is this a lot? Is this maybe reasonable? Again, you can take different stands on it, but I mean, you need to get the information in order to be able to make these stands. But importantly, these operations are typically run very few times. I mean, they take a lot of time. They're very expensive. But what about normal quote-unquote experiments? I mean, training a small model or maybe fine-tuning a model, these are far, far cheaper, but these are run actually hundreds or even 1,000 times a day by different researchers around the world. So how can you accommodate for the cost of all of these experiments? And perhaps most importantly, what about inference operations? Inference are very, very cheap, though becoming increasingly more expensive, but maybe they're run billions of times a day or even more. I mean, think about AI operations that are running in every Google search that you make, or every Facebook or Twitter post, or every TikTok video that you upload. I mean, these are very, very frequent operations, and AI is becoming more and more dominant in all of these operations. And indeed, there are some estimates that say that AI computation is mostly composed of inference. Some maybe talk about even 80 or 90% of the AI computation is spent on that. I mean, it's extremely hard to make these estimations, largely because these large companies don't want to disclose them. They consider them proprietary secrets. But I mean, again, the same conclusion holds. We need better reporting in order to get a good understanding of the carbon footprint of this technology. So one last thing along this topic, when we think about the carbon footprint of AI or NLP, something that's often neglected, but I think is also worth considering, is what about our conferences and the conference travel? I mean, we have conferences in various beautiful locations around the world where thousands of attendees from different parts of the world are flying in mostly to attend, and these also result in substantial carbon footprint. Jacob Eisenstein and myself try to estimate to answer this question exactly and estimate the carbon cost of having NLP conferences. And to do that, we started by taking some conference, say maybe someone wants to guess or maybe knows which city is this and which conference it relates to. I don't know if people have any guess. Well, I'll tell you, this is Toronto, where ACL 2023 was held. So we took a conference like ACL 2023, and we got the list of attendees, more accurately, the addresses of the different attendees that went to this conference. And we sorted them by the number of attendees from what we're seeing here is the number of attendees from a given city in a given country. And for each of these locations, say Jerusalem, we got a list of the closest airports to that location when we assumed, again, definitely a rough estimation, but somewhat accurate, I hope, that all people that came to the conference from this city went through one of the close by airports. And then we got open source flight information, and we computed the shortest path from each of these airports to the target city, in this case Toronto, and we computed the carbon cost of having such a trip. We aggregated it, and we got a number that gives us an estimate of how much carbon a given conference, or at least the flight component of a given conference, consumes. And when we look at the numbers of specific conference, so before we get started, I mean, here are some baselines. This is roughly how much carbon was emitted by training Llama and Llama 2 models, at least as reported by the authors. We see that Llama resulted in 1,000 CO2e metric tons of carbon, and Llama 2 with 500 of the same quantity. And this is the same amount for the 2023 conferences. ACL 2023 resulted in 2,400 metric tons, and EMNLP 2023, which was held in Abu Dhabi, resulted in 5,000 metric tons. So somewhat intermediate conclusions that NLP conferences are responsible for substantial carbon emissions and span roughly between 2.5x and 10x of our largest LMs, at least as reported by the authors. Another thing to notice is that the location matters a lot, because having a conference in Abu Dhabi is twice as expensive as having it in Toronto. And you can talk about the reason for that, and maybe maybe there are different constraints of why having a conference in one location versus the other. It's definitely a good idea to have conferences not only in North America, but still there are definitely costs to having them in remote places. And we repeated the same experiments for 2023, two conferences reaching roughly the same conclusion. Again, the location of the EMNLP 2023 was held in Singapore, and it was about twice as expensive in terms of carbon of NACL 2023, which was held in Seattle. So kind of the high-level takeaway here is, again, NLP conferences are definitely a source of carbon footprint, and we have some potential suggestions of how to mitigate it by allowing authors to attend which conference they want to, given that they have a paper accepted. I think in the interest of time, I won't go into too many details on that. But kind of to summarize, we talked about Red AI and the concept of making models larger and larger in order to improve them. And we've shown that it both leads to lack of inclusiveness and to environmental problems. Before I continue, any questions, or is anything anybody wants to discuss?
If you want, Roy, we can keep the questions till the end. What do you think? So people can write in the chat their questions and we can give them the turn to speak. What do you think?
That sounds great. I mean, if anyone wants to jump in, you're more than welcome to, but I can also wait to the end. Sounds good.
Perfect.
Okay. So let's move to the second part of the talk, which is the part about green AI. And again, in the green AI, we're talking about, I already mentioned the part of our reporting and then why this is important. So now I'll mostly talk about efficiency. So the first thing we did in that paper is ask whether typically AI research is focused on accuracy or efficiency. And this is a study we did again in 2019 or 2020, and we picked 3 conferences and sampled papers, and found that most papers that we sampled focused on accuracy much more than efficiency. So basically, at least then, a few years ago, accuracy was a much higher topic of research for different researchers compared to efficiency. And in the few years that passed ever since, a large thing what I was trying to do with in my own research and in my own effort is to get more people involved in working on efficiency. So this included working on and building an efficient NLP policy document that was approved by the ACL. This includes some recommendations like setting up conference area as a target efficiency, basically having a place, if you want to work on efficiency, you have a place to submit your work to in the regular NLP conferences. And giving incentives to authors to release their trained models and to release their weights and their outputs and a bunch of relevant details about their experiments. We also ran a DaSCI event. For those of you who are not familiar, DaSCI is a beautiful area in Germany where you have small conferences on a dedicated topic. So we went and ran one on efficient and equitable NLP in the age of deep learning, and had some really impressive lineup of attendees. And one of the outcomes of this was a survey that we wrote on efficient methods for natural language processing, which outlines, I think, a very broad picture of the different ways in which NLP can be expensive, and ways that and opportunities for making it less expensive. So if you're interested, you're more than welcome to check out this paper. It was accepted to tackle about a year ago. And I think much of the content there is still very relevant. Okay, so this was a short, this was the first part of this talk where I talked about basically the concept of red AI and green AI. So now I want to move to the second part, which is talking about two of our most recent findings on efficiency. And I'll start with the first, which talked about reducing LLM memory footprint. So the work that I'll be covering here is titled Transformers or Multi-State RNNs. This is work that we released maybe 2 months ago or so. It was led by two of my students, Matanel Oren and Michael Chassid, and along with our colleague Yossi Adi. To give a couple of minutes of background about this work, nowadays transformers are the most dominant tools in NLP, but those of us old enough to remember that until maybe 7 or 8 years ago, we used to have recurrent neural networks as the most dominant tool. And in recurrent neural networks work quite differently than transformers, allegedly differently. If you look at the figure here on the right-hand side, we basically have, in order to represent if these dots are considered as words, and if you want to represent the hidden representation of a given word, we get two types of inputs. We get the previous hidden representation from the previous layer, and the hidden representation of the current layer from the previous token. And this is how we go in each step. We compute this representation based on these two, and then we move on to the next one and compute it based on these two, and so on and so forth. Mathematically, you can also look at it similarly. The function of an RNN at layer L gets its input the value of x at time t at layer L, and this should be L minus 1. This is a mistake, and the hidden representation at time t minus 1. So this is these are RNNs. Transformer, on the other hand, work a bit differently. And this is the original figure from the original transformer paper. And importantly about transformer is that the only component within the transformer that has access to other tokens is the attention mechanism. And the attention mechanism, unlike RNNs, where you only have access to the previous token in the document, in transformer we attend to all the tokens in the document. So if we're now working with token n, then we attend to all the different tokens from 0 up to n inclusive. And this gives us potentially the ability to hold long range to model long range dependencies and reach information from previous part of the document much faster. So again, allegedly they look very, very differently, transformers and RNNs, and I'll try to convince you that maybe they're not that different. But before I do that, I'll mention one last thing about the way transformers are being used today. They're mostly being used in LLMs as decoders. What I mean by decoders, it means that that LM decoders are trained to predict the next token in a sentence given a prefix. And these decoders decode autoregressively. So let's look at an example. So if we have some prefix of consider these 3 tokens, then we generate the next token at this point, and then the next token, and then the next token, and so on until we reach the end of the sequence. Now, these two concepts are quite important, and this is how they are being used nowadays in LLMs. And another final thing that is important to notice here is that one of the biggest computational bottlenecks of transformer LLMs, decoder transformer LLMs, is that you need to cache all the representation of all the previous tokens that you attended to. So here in this example, so we start in the first part, we attend to these three tokens, and then these 3 tokens plus another token, and every time we add another token. And so in order not to recompute all the previous tokens that we already processed, we keep their representation in memory. So this means that as we generate more and more tokens, we consume more and more memory. This is the standard way of using transformer nowadays, and this is again one of the biggest bottlenecks. So after following this this introduction, I hope it was relatively clear. I want to move to our contribution, which is an expansion of a standard RNN from regular RNN to what we call multi-state RNN or MSRNN. So now let's define an RNN with a that instead of working with vector states, works with matrix states. So if this is the previous representation of an RNN that the previous equation that I showed you earlier, now let's replace this hidden vector, again, the vector of the previous token, with some matrix. Now the definition is exactly the same, just instead of working with vectors here, we're working with matrices, and we get as input a matrix and we return a matrix. Now, importantly, the dimension of this matrix is parameterized by D, which is the hidden state, but also by some function G of the time step T. Now let's talk about different values that this G can get. Now, the first thing that I'll try to convince you is that transformers are actually infinite MSRNNs. And what I mean by infinite, now let's define transformers as MSRNN with setting the G and this G function of T as just equaling T. This basically, what does this mean? This means that basically at time step T, this matrix is of size 1 over D. At time step 2, it's size 2 over D, and 3 over D, and 4 over D. So every time we add another row to this matrix. And so now we can, and now let's look at transformers and define the hidden matrix in terms of the key and value matrices of transformers. So we can define the hidden representation in our MSRNN as the key matrix and the value matrix. And now when we get another key and value, basically we generate a new token, we get a new key and a new value, and then we just add them as a new row to our matrices. And as a result, every time we get a new token, we get another row to our matrix, and our matrix become larger and larger and larger. So in this sense, it is infinite because it can grow infinitely. This is one example here. So if you think about all this green area as our as one big matrix, maybe you think of it as here it looks like different columns, but it's actually different rows. And so every time we generate a new token, we get a new row to our matrix, and so on, and we can generate as many tokens as we want, potentially infinitely, and get an infinite state matrix. Is that roughly clear? Okay, so transformers are potentially infinite MSRNNs. I mean, you can run them infinitely and generate an infinite context window. But what I'm trying to show you now is that they're not, while they're potentially infinite, they're actually being used as finite MSRNNs. Basically, when you set GT to be the minimum between T and some constant K. So we don't allow the model to go infinitely, but we stop it at some point K. Now, this is how LLMs are typically trained and evaluated. LLMs, if you take Llama, for example, a typical RNN LLM, it is trained with a context window of 4,096. This means that at train time, we're giving it 4,096 tokens, and then we break. We don't allow it to observe tokens from previous history, but we do it in chunks of 4,096. And usually at evaluation time, we do the same thing. We allow it only to generate up to 4,096. Because otherwise the model gets into various problems, one of them being that memory just keeps growing and growing. But what I will show you now is that we don't need to consider the maximum value. We can also compress the RNN in this way, decrease the amount of cache, cache that is used by the model with some compression policy. So let me give you a few examples of such compression policies, and I'll try to use. If you look at consider this notation, I hope it will be clear. Where each of these is one cell in our multi-state, one state in a multi-state RNN. So this is how transformers are typically used. You use all of the tokens in your previous history until a given fixed size. Now, one thing that you can do, and it's been done in the past, is to what is called window attention, which means that you only keep the K recent representation in your multi-state. So this would look something like this, roughly. everything in your far history is being deleted, and this window keeps moving, right? I mean, you would start with this will be the first say if this is 5 or 6 is your window size. Then you start consuming tokens until you reach it, and then you get another one and drop the last one, get another one, drop the last one until you reach this point. Now, another way of doing this, which works much better than window attention, is what we call window plus I. This is the same as window, but also keeping the I initial tokens of the sequence. Now, for some reason, this is very important for an LLM transformer, and allocating your budget such as you keep always the first between 1 and 4 tokens, and the rest you allocate to the last part works much better than this window variant. And you can also consider more advanced methods. This is a method called H2O, which also uses the most recent tokens, but also allocates other tokens based on the largest accumulated attention score throughout the sequence. So you have, these are fixed, and these are the attention mechanism is used to select which tokens are being used. So these are different compression policies, and I want to show you another policy that we introduced that, and I'll show you that it works better than the previous policies. So what we do is we also use the attention mechanism, but in a different way. So if this is the maximum size of our compression size, and so we start with 5, say 5 token, and we want to consume the 6th token, we have to drop something. So we drop the token with the lowest attention score by the last token. So for instance, here, if in this step we have 6 tokens, this is the one with the lowest attention score by the final token. So we just don't keep it. We can move to the next step. You see this is grayed out, so this is not kept in memory. And again, we repeat this process. Again, this time, this is the one with the lowest score, so we drop it. And this one, this is the lowest score, and so on and so forth. And every time we keep a fixed size cache, but we let the approach be fully data driven. We don't keep an initial set of tokens. We don't keep the last set of tokens. We just let the model decide based on what's most important for the last token. These are the tokens that we keep. Now, importantly, this is a very simple method. This is a torch-like implementation of our method. We call it TOGA. I won't. You don't need to carefully read it. You just have to you just need to notice that it's very short, 5 or 6 lines of code. This is what it takes to implement our method. Okay, so I present a new method. Let's see how well it works. So we ran some experiments with a bunch of the benchmarks. We started with language modeling on long text using the PG19 benchmark. We considered 3 different LLMs for these experiments. We also ran some long-range understanding tasks using 2 benchmarks. One is a summarization benchmark, and another is a question answering one. And we also did a long text generation that, in the interest of time, I won't go into the details here. So let's look at our results. So we start with language modeling. This is the results on the PG19 from the HUJI model, which is a common LLM. The y-axis is the perplexity. Basically, lower is better. We want lower perplexity. And then the x-axis we see different compression ratios. So 4096 is the base cache size. That this is what the HUJI model was trained on. And we see what happens when you decrease it in exponentially decreasing size. If you only allow 22,048, 1,024, 512, and so on and so forth. And we have similar tables for the other LLMs with the same data set. So you can notice here, and the different lines are the different methods. This is the baseline of never mind what the baseline is, that it works very poorly. This is the window approach that I've showed you. This is window plus I, which in this case it is 4. This is the H2O model that I've showed you. And the top line is basically using the model with the full context. So this is the dashed line. And TOVA, our method, is the blue line. Now, as you can notice, when we use TOVA, we get comparable results using only 1/8 of the cache size. So if you look here at 512, where we lose maybe up to less than 1.5 perplexity point, with 512 compared to 4096 in all three cases. Now, so these are the results for the language modeling. This is the result for the summarization model on the S-quality dataset. On, again, three different models, same baseline. We ran only the baseline that worked well on language modeling. So we have the WINO plus I and TOVA and our top line. And again, same trend. Our model does much better than the other policies. And if we allow 1 point degradation, we're able to get between 4x and 8x improvement in the amount of cache that we keep. And finally, the QA, the question answering data set, which is a harder data set of a retrieval data set. Here we also see that TOVA does much better than all the previous baselines, but we need roughly 1/2 of the cache size to be comparable to the top line. So still 1/2 is not is definitely a meaningful save, but not as good as the previous experiments. So kind of to summarize, we've seen that transformers are multi-state RNNs. They're theoretically equivalent to an infinite MSRNN with a growing multi-state size that potentially grows infinitely if you don't stop it. They're practically used as finite ones because in practice we use them as finite. We cap it at 496 or whatever, and we show that they are not really using their full context. They can be compressed quite substantially into much smaller cache size, and then by that, this allows us basically, on the one hand, to better understand transformers. Now we know that have some connection to RNNs, but also to get huge potential for memory savings, potentially saving up to 7/8 or 87% of the cache size. And this allows us also to use you can either use it to save memory or to run a larger batch size, which makes your model run faster on multiple examples. This is the part about reducing LLM memory footprint. And now I want to move to the final part of this talk, which asks, can we sell for smaller LLMs? So this is a work that, again, led by students Michael Hasid, along with colleagues Tal Remez, Jonas Gering, and Yossi Adi. And the title of this work is the larger the better, improved LLM code generation via budget reallocation. And the gist of this work is quite simple, actually. So say you have a large language model and you want to make it better. So as we've discussed during this talk, a simple way to make it better is just to use a larger model. Say if this is our original model size, take a model that's 10 times larger, you'll get a model that generally works better. And now the typically way we would use these models is to run them once to get our prompt and just use them to generate our output. But an alternative way to increase budget and get potentially better results is to take our small model and run it 10 times. Now, the underlying assumption here is that the cost of generating 10 generations is the same as of a small model is the same as generating 1 generation from the large model. This is not 100% accurate, but it's a very good approximation. So basically, you can think of a trade-off between running the large model once or running the small model multiple times. And so we wanted to ask this question: what is better? What is given that you have a given computation budget? What is the better way to allocate it? Using the larger model with fewer times or the smaller model with more times? So to do that, we considered, we ran a bunch of experiments. In particular, we focused on code generation tasks. So in code generation tasks, your input is some description of a function or a piece of code that you want to implement. And your output is some program in some programming language. Now, importantly, we used a common setup for code generation is a case where you have unit tests for evaluation. So we basically, you give it as input a code description, and an output is a program. And the way to evaluate whether the model works or not is not by looking at the code and trying to decide whether it does what we want it to do, but we run some unit tests. And if the model passes the unit test, then we say that it has succeeded on a task. Now, this is important because this allows us to take multiple outputs from our small model and see whether one of them works, because we can take 10 outputs from the small model, run all of them through the unit test. If one of them at least works, then we're good. So let's see how this works. Let's talk a little bit about the experiments. We ran experiments with the code llama models of different sizes. We have sizes 7B, 13B, 34B, and 70B. And we used 5 code generation benchmarks, human eval, MVPP, and 3 versions of the apps tasks. And we used 2 budget constraints. We basically say that we allow them to, we want to keep the budget fixed. So how do we define a budget? We say that either they have the same floating point operation budget. Basically, you run the large model once and compute a number of floating points, and then run the small model until it reaches the same amount of floating point, or the same for time. Say the larger model takes 10 seconds to run, and so we run the smaller model enough times until we reach 10 seconds, which would roughly be 10 times. Okay, so these are our experiments, and I'll start with our conclusions. Small models often outperform large ones. So let's look at some plots to illustrate that. Now, this is the first plot. This is the usually reported measure of pass at k. What does pass at k means? It means that if you allow the model to generate k examples, how good would it do? I mean, and again, using the unit test as an evaluation measure. And here we see that, not surprisingly, larger models do better than smaller models if you don't account for, if your budget is the amount of generations. But if you do include how much each generation costs, and basically you control either for the floating point operation or for the wall time, you see that actually using a 7 and a 13B model is much better than using a 34 or 70B model. You see that there's a very large gap in both cases that says that if you have a fixed budget of number of floating point or of wall time, you're better running multiple iterations of the smaller model, either 7 or 13, than fewer generations from the larger models. Now, finally, I want to ask, what if we don't have unit tests? What if we assume that we can take all the outputs that we get from the smaller model, and if one of them works, we can know it because we can run the unit test. But this is not always the case. I mean, in language tasks, we don't have an oracle that tells if one of the 10 generations is better, and if in some cases even in code we want to get one answer and not 10 answers. So we took a simple approach and used another LLM to rank the 7B model outputs. So if the 7B model provides us with 10 outputs, then we use another language model to rank them and to provide scores, and then we get the best one, and this one is the one we compare with the largest one. And here we see that this doesn't work as well as in the previous case. Here we see what happens when we rank them based on larger and larger models. So as the NGO ranker becomes better and better, the results improve. But the 70B models and also the 34B model are still far better than running multiple iterations and choosing just one from the smaller model. Okay, so I think this is where I'll stop. I'll just summarize briefly this talk. We started by talking about what is Red AI, the practice of taking models that we want to improve and just making them larger. We talked about different problems that this creates, both in terms of inclusiveness, because very many people cannot afford to work with this practice of just making things bigger, and also about potential environmental aspects that this creates. And we talked about various consideration when considering this aspect. We then talked about green AI as somewhat an alternative to red AI, where we not only try to improve the model, but also try to make it smaller or more efficient. And we talked about the importance of reporting in all of this. And we talked about 2 of our most recent results on efficiency. One reduces LLM memory footprint by compressing the model cache size. and the other by running in multiple instances of a small model rather than one instance of a larger model. No, that's it. And I want to thank you for your attention, and I'm very happy to take questions.
Thank you very much for this very, very nice talk. So now it's time for questions from the audience. So as usual, feel free to write your name in the chat and I'll give you the turn to speak. Any questions? Okay, well, first, Andres Herrera. Okay, so please go ahead.
Yes, first, I wanted to thank you for the talk. It's been really, it's covered a lot of topics in very little time and in a very understandable way, and it's been a pleasure to hear you. I wanted to ask about your results on reducing the memory footprint. So as far as I understood, basically the point is you don't have to keep in memory all the tokens, right? You only keep, let's say, 1/4 of them. However, the attention mechanism is still applied to all the inputs, right?
No,
and as far as well, I mean, as in maybe not to the ones that you haven't kept in memory, but it is still applied to all. I mean, it's only applied to all the ones that you've kept in memory, right?
They're only applied to the ones that are in memory. So if you fix it on 500, it only considers 500 tokens. The others are ignored. I mean, they're not saved in memory. Then I mean, it's meaningless to consider them anymore.
Yeah. So my point is, the size of the attention mechanism is fixed beforehand, right? And the attention mechanism is doing a product between the matrix of, as far as I understand, of the queries and the keys, right? So there is no way you can avoid that product of the queries by the keys. Is that right? So even if you don't keep those words in the memory, you still have to do that product, and that's the size of that. Let's say window that is the input of the attention mechanism is the same. I mean, I guess your method works if you train a transformer with a smaller window for the decoder.
So I hope I understand the question. So please let me know if I missed anything. So you're asking whether, I mean, you're rightfully saying that this mainly affects the query and key and value matrices. And the query is always a vector, actually. It's the keys and the values. And basically the effect of what we do is just by decreasing the size of the key matrix and key and value matrix. So the way attention works practically is that by attending to multiple tokens means multiplying with a large matrix, large key matrix. So if we make the key matrix smaller, then we're multiplying by fewer elements. Now, this is maybe a follow-up question to what you maybe want to ask, whether this also results in a reduced runtime. And we actually found that it doesn't really help with runtime because this is done very efficiently on a GPU. So reducing 4,000 matrix of size 4,000 and 500 is done. It runs roughly the same time, but we're definitely reducing smaller and smaller matrices. I hope this answers your question. I fully understood it.
Yeah, that helped. But my point is really that the transformer has been trained on a large window size, right? And therefore, that memory is already, let's say, saved in the GPU. Is that right? If I maybe I'm talking about the vanilla transformer, not the one you're using on your experiments.
No. So maybe something I haven't mentioned explicitly. So I'll say it here. This is a good point to say that we don't modify we don't fine tune a transformer. We don't do anything. We take a transformer off the shelf and run it as is. So this is so thank you for reminding me to say that. And the size of the GPU memory, the cache memory, is directly controlled by the amount of tokens that you currently process. Now, the transformer has been pre-trained on 4096, say, and it has the potential. I mean, so during training, it saw always 4096 and had to keep it in memory. But at inference time, maybe I'll go to one of the this. Let's look at. Can you see this? So here, when you're generating the third token, you only have three. The size of the matrix, the cache matrix, is only have three lines in that matrix, 3 rows in that matrix. So the size of the memory is relatively small, but as you consume more and more tokens, the size of this size grows more and more. So what we're doing is that we are capping it at the lower, capping it at say 512. So you're never going. This matrix never grows beyond that.
Okay.
So
thank you.
I hope this was clear. I'm not sure if.
Okay. Yeah. I see how they can do that.
Yeah. Thanks for your question.
Okay, thank you very much. So now we have another question from Darren Winter. You rightfully point out the costs about AI and the invitation for discussion about the true cost of AI. But do you agree that the majority of people do not feel they have the power to make any difference, and larger corporations, regardless of our protests, will just continue to grow technology for dominance and pass the costs to us? Do you think this cycle can be broken, and if so, how?
And thank you for your question. This is a good one. Let me try to. I think I'm not sure what exactly you mean by. I mean, so we need to kind of discuss what is the problem with growing the technology. I mean, I think we're all trying to improve the technology, so it's not necessarily bad to grow it. Maybe you're referring to growing it in size and passing the cost as in the carbon cost and that sort of thing. And I don't. My experience was that. I don't think people in large companies are trying to do bad things. I think they might end up doing bad things even though they're not trying to. But they're definitely affected by the scientific community and the larger public. So if you look at this blog post that I pointed to from Google, this one, I think it came after, I mean, the Emma Struebel's original work and our follow-up work on Green AI was definitely a spark for them to be more open about how much carbon their technology consumes. I mean, I know that because they were in touch with us regarding this draft. I mean, they are trying to listen, and they are trying to. I mean, they care. Maybe they care about the PR rather than the. But I don't know. But I mean, at least I mean, as an academic community, we're able to grab their attention along these lines, and I think this is becoming more and more common for even big companies to be more transparent in the amount of carbon that their technology requires. So in this sense, I think they're listening, and they're definitely. I mean, they're also. I mean, I've been in touch with U.S. senators and British Parliament representatives about regulation of the carbon elements of AI. So there are definitely things to do, even within academia, even though I agree that, I mean, big corporations are hard to, it's a very large shift. It's very hard to move from its course. And obviously what they care about is their revenue. But then I don't think it means that it's hopeless. And at least that's been my experience. I hope this answered your question. Yep.
Thank you very much. Any other question? Any other question from the audience? No? Okay, so I guess I have the last one then. As you said, something that it may seem a bit surprising, but 80% to 90% of the cost of a neural network is in inference rather than training. So I'd like to ask you, where is the research effort usually focused today when talking about efficiency? There's more research on training, on improving inference. What can you tell me about this, please?
Yeah, so I mean, thank you. This is a really great question. So the numbers 80-90% come from a blog post from NVIDIA. I mean, I'm not sure. I mean, how? I mean, basically means that, I mean, if you think about the efforts worldwide, where some people are building models, some people are running models, their estimate was that about 80 or 90% of the energy is used on running them, which I think makes sense if you think about these huge companies that build their tools and then lots of people are using them on a daily basis or even hourly basis or even more frequently. And I think to your second question, also I think this aligns with much of the efforts that we're seeing, and at least my personal efforts, and I think the efforts around that I'm seeing, because so few people can afford to train these models, then I mean it makes it's hard to make real progress on an academic budget, and so I think it makes, and on the other hand, there's a lot of impact if you can get the models to run faster. I mean, I think that both of the examples that I give here were examples of inference time. In most cases, we took off-the-shelf models and didn't touch their architecture. Some places, I mean, the distillation is kind of, it does train a smaller model, but this smaller model is still, I mean, it's mostly useful for inference. I mean, this is not to say that there aren't any efforts around training, but I think inference is the more important problem, to be honest, nowadays, and I think it's getting more effort.
Okay, so thanks a lot for your answer. I don't know if there's any other question from the audience, because otherwise we can end here this DaSCI seminar. Last chance. Any other question? No? Okay, so we can end here this DaSCI seminar. I want to thank again Roy for accepting our invitation and for giving this very nice talk. And thanks as well to all attendees for the questions and comments. So thank you very much. Thank you very much, Roy.
Thank you for having me. I was had a lot of fun. Thanks.
Our pleasure.